wants to perform surgery in a car. And
Y'all had a good weekend, folks? Remember, we're going to have an exam on Friday, right? Friday? Yeah, so we're going to wrap this up, and then we'll start on Chapter 6 today. But Chapter 6 is really short, and hopefully you've already done those first few little things for Chapter 6, those screencasts. Y'all done those?
Is there meant to be a cat video?
A what?
Cat video?
Yeah, I think that I was looking for a different video, but I couldn't find it, so I thought, well, shoot, I'll just put it in this.
I was like, I don't think this is I watched like 2 minutes of it, I stopped watching it after that.
Yeah, it was really just a joke.
Okay.
Yeah.
cat video.
Did y'all watch the cat video?
Cat really?
Yeah, okay, y'all haven't seen it yet, have you? What's that? Right, yeah. Alright,
I'm sure he was letting his throat.
Whenever you start, can you start by explaining a little bit more about the Einstein?
yeah, we'll start it soon. Alright, so here we have a mass spectrometer, 2 particles, same mass, same speed. Follow these. Which has the bigger charge? They follow these paths. I want to remember our cyclotron equation. R equals mv over qb. Which has the bigger charge? About 10 more seconds. 55. Stop. Let's see. So pretty split between A and B, but if we want one that has a big charge, if Q is big, that means R is small. So B is the right answer here. All right, proton enters a magnetic field. It's perpendicular to the velocity. What happens to the kinetic energy of the proton as it travels in this magnetic field? Remember, what type of force is a magnetic force? We call that a particular type. It's called a what?
Conservative.
Okay, it is conservative. What else?
Centripetal force?
It's centripetal, right. And what does that do to the kinetic energy? Centripetal force. All right, stop at 58. 58. C is right. This is a centripetal force, all right? So the velocity vector is in this direction, and the magnetic force vector is in this direction. Not magnetic field, I'm sorry, magnetic force. And so it's always perpendicular. That means it only changes the direction of the velocity, not the magnitude. That's what a centripetal force does, causing it to move in a circular path. If it doesn't change the magnitude, it doesn't change the energy. All right, here we have this is like in a CRT. You know what a CRT is? Those old televisions, the cathode ray tubes, the big televisions like the big wooden cabinets. Yeah, they use both electric fields and magnetic fields to direct a stream of particles to the back of the screen. And then depending on where those charged particles land, they're particular dyes in the screen or whatever, and they phosphoresce, I think, causing a particular color. So this is a pretty common thing to use magnetic fields and electric fields to direct a stream of particles. And here we have an electric field acting on a stream of electrons. And so the electric field gives a force The electric field is up here. What's the direction of the force on the electrons due to the electric field? Not the magnetic field, the electric field. Not a right-hand rule thing. You use my thing there, Wayne. That's my sign. The middle finger. Yeah, that's my sign. Yeah. Oh, what is the direction of the electric force? Now think back to chapter. Right. Down, right. So the electric field is up, and so the electric force is down. Remember, electric field gives a force on a positive particle in the same direction as the field. Chapter 2, I think, or whatever. So that means in order for this stream of electrons to keep going straight, the magnetic force has to be what direction? Two forces acting on. The magnetic force has to be up. So FB has to be up. And so now what type of magnetic field will cause this magnetic force to be up? You follow my question? No one understands you. Right. All right, there are two things going on here. I have this stream of electrons. They come in, and I want to modulate their direction. I want to change their direction to go in whatever way I want. And so I can apply a couple different forces to it. I can apply an electric force to it. I have this electric field that's drawn here on the page, and that electric field causes the force on this negative stream of particles to be down. So there's an electric force. This is not a magnetic force, it's an electric force due to the electric field. Like you can imagine, you have these two metal plates, right? There are electric fields going in between the two plates. However, in order to make this stream of electrons go straight, there has to be a magnetic force that's balancing the electric force. And then it just goes back to one of our right-hand rule questions that we've been having. If I have a force that's up, a velocity that's to the right, what is the direction of the magnetic field that's causing that? It's the common thing to use magnetic and electric fields together to affect the direction of a string of particles. Don't forget that they're negatively charged. So all right, about 10 more seconds. 3:35.
I guess that's not the right answer.
Okay, these are negative particles. Did y'all take that into account?
You just said it as like a.
Yeah, so it's right if they were positive, but D is the right answer. It's out of the page. Yeah, so imagine, I have this force, my magnetic force is up, my velocity is to the right, and so it would be into the page, except that they're negative, so it's going to be out of the page, the force, because we have a negative particle. Right, so it's opposite. Okay? Then we have a wire with a current in it. What's the direction of the force on the wire? Magnetic field is up. The magnetic field is up, right? So the magnetic field is in this direction. Current is in this direction. The magnetic field is in this direction. I remember more correct is not to say the current is in that direction, but the length of the wire is in that direction. All right, a few more seconds. Starting at 118. That's not right, is it? Oh yeah, that is right. Yeah.
So almost the whole class got it wrong.
Right. That is right. Here we go. Wire up, magnetic field up. A few more seconds. 38. All right, very good. When they're parallel or anti-parallel, it goes to 0. Remember that force is ILB sine theta, and so the sine of 180 or 0 is 0. You didn't know anti-parallel? I should try to use that word today. People don't use it, huh?
You didn't say the anti-parallel word in past lectures.
Oh, really?
You said parallel.
I'm sorry. Well, parallel or anti-parallel. That's a word that we don't use enough. I think we should try to use it like in this, I went one way, but you were going anti-parallel or something like that. Yeah.
What do you mean by that?
Oh, these two lines going both this direction are parallel, right? Because they're run alongside one another. But if you have one going one direction like this, those are
So they're
anti-parallel. Opposite direction. Yes. Or what? Or anti-parallel.
I saw what you did.
All right, what's the direction of the net force on this loop? The net force. And this is a loop, a current loop. You might not be able to see the arrows, but the currents are flowing in these directions. Looking for the net force here. And don't think too hard about it. The net force. All right, so a few more seconds. 105, we'll stop. What's that? Yeah, we had some more. All right, C is right. The net force, because whatever force acts on one side is on the other side is opposite that, or anti-parallel to that. Yeah, so they're gonna, all those vectors are gonna add up to 0. All right, now let's consider this. Here we actually have a loop that is rotating on an axis like this. We've had a similar question to this. I want to know what direction will this little motor, this electric motor, which way will it rotate? At least initially, which way will it rotate? Because if you let it keep going, it's going to flop back and forth, right? Unless you change the direction of the current. It's not that easy, actually.
It's actually kind of. I figured out a really cool way to make it easy. You just kind of redneck it all. Like, I really thought of a way that you can do it with the popsicle sticks, and you kind of make it how they do make it with the wraps, how they do it since they separate them in different lengths, and you can even make the brush and the things by using kind of like a little bit of copper wire and kind of like your own little brush where you hammer on some small little copper plates.
All right. Well,
Because I have all those things actually just.
all
My
right.
parents are
You
weird.
work on that, man.
My parents are weird.
All right. A few more seconds. 1:15. Okay, very good, clockwise. C is the right answer. You can take either side, like for example, you could take this side right here, where the current's in this direction. So have a current that is into the page. Or as I say the current, really we're talking about L, because current isn't a vector. Really we're talking about the vector L. And then the magnetic field is in this direction. And so the force will be down in this direction. So I'll get a clockwise, a force pulling down on the right and a force pulling up on the left. So it's going to cause it to go clockwise. What's the direction of the magnetic field at point P? These are two wires, one on the left going into the page, one on the right coming out.
Oh.
All right, just a few more seconds, 1 minute, 1:03 we'll say. All right, let's see. So due to this one right here, the magnetic field is what? Counterclockwise? Is that right?
Yeah.
All right, so it looks like that. And then due to this other one, it is clockwise, so it looks like this. So at point P, due to here, I get a magnetic force or magnetic field that is in that direction. And then due to this other one, I get a magnetic field that is in that direction. But that magnetic field is not zero. Y'all follow? What's going to be the right answer then?
C.
C is the right answer. If I have two vectors, I have one vector that's in this direction and one vector that's in this direction. If I add those two up, I get a vector that's in that direction. All right, let's try this next one. Actually, I'm going to just, here we show the vectors. On this next one, I'm just going to go through. We've done these before. I wouldn't expect one like this on the test. There's it takes a long time to do these. So I'm going to step through just one of them. I'll show you which one it is. The answer here is B. Which one has the greatest magnetic field? And you want to take each one, and like for example, I have this one right here, and the magnetic field due to this one is clockwise. So it looks like this. And then similarly, due to this one, is also clockwise. All right, so if I were to take the magnetic field at this point, due to this magnetic field, it's going to be in that direction. Right, because that vector is tangent to the circle. How about this one, the one on the right? What is the direction of the magnetic field at the middle? It's going to be sort of up into the, like at this point, it's going to be in this direction. So if I translate that vector over, it's going to look like that. All right. Maybe B might not be the right answer here. Let's see. Now, down here, this is coming out of the page, so these magnetic fields are going to be counterclockwise, like that. And let's see, due to this one on the left, it's going to be up and like that. And the one here at this point is going to be down and to the right. All right, so the magnetic field here is going to be to the left. Now, if you look at all these others, the magnetic fields, if you add them all up, look like this, and those then have a net magnetic field of what? Right, both of these have net magnetic field equal to 0. We've worked problems like that in class. I wouldn't expect one with so many wires that you have to find, but you probably will have one with, 2 or 3 wires, and I just ask you the direction of the magnetic field, kind of like that previous question. This idea that these wires generate a magnetic field that surrounds them. There's all the vectors. All right, so I have a positive charge that moves parallel to a wire. If I turn on a current in the wire, I have a wire current moving in that direction. If I turn on that current, that charge will feel a force. What will be the direction of the force?
Your ConcepTest 6.5 on in the next chapter, farther ahead because we've already been through. We're gonna just give it a fly past real quick.
Not that far, but yeah.
Laser. Laser. Make it easy. You cropped one in.
Cropped one in.
Freaking laser.
Oh yeah. All right, guys. Do 130. 130. All right, so the magnetic field due to this wire is out of the page. You have velocity up, magnetic field out of the page, so it's going to be to the right, which is to the plus x, you're right. So the force that it feels is to the plus x. So C is the right answer. Let's say we skipped this, remember, the force due to 2 parallel straight conductors, right? We did skip that section?
Mm-hmm.
Yeah.
It wasn't that hard to figure out.
No, it's not that hard, actually. But and now, what is the direction of the magnetic field at the center of the square loop? You just use the curl rule for this, like we did with the, you just take one section. It's like a solenoid switch. Did we watch the video of the guy with the solenoid switch? The British guy? Did we watch the video of the guy with the solenoid switch? Okay, I'll show it to you right quick. It's kind of...
Problems like I also can't remember yesterday.
All right, about 10 more seconds. 5 more seconds. Stop at 110. Okay, it is E, out of the page. Just using your curl rule. You just take one section of it. So say we take this section, for example. Your thumb goes in the direction of the current. It goes into the page and then out of the page. So we had experienced a current on this side. And then if you follow around, experience a magnetic field that would be out of the page. And then if you follow around each of the 4 sides, they'll all generate the same magnetic field. So we're going to get magnetic fields that are out of the page, all around the loop, or excuse me, into the page, all around the loop, and then out of the page in the middle of the loop. And that's what allows for a solenoid switch, because you have this magnetic field that's all in one direction inside the loop, and it can interact with whatever's inside the loop. Let's watch that little video This is just a British guy. He's using a type of switch called a solenoid switch. But this is actually a solenoid valve.
What do you call it?
Yeah, it's 55, 56, and 57. So if you...
Those are like chapter 2, guys. Going to 55, 67.
Let me show you.
It was like 102 screen casts.
They were, yeah, but for this chapter it's the same. So we're looking at 55, 56, and 57 right here. They're also linked on that website that I gave you, the playlist. All right? Don't sweat it if you didn't watch it yet, but you need to go back and watch them. It's just like 20 minutes or so, right? About 20 minutes? Everybody saw them? Or, okay. Well, make sure you see them before Friday, because you'll see some material on the exam that's from that. But you need to know about the history of the nature of light. That is, how light has been viewed either as a particle or a wave, and why it's been viewed that way. Newton viewed it as a particle because of reflection, because that's what particles do. Huygens saw it as a wave because of refraction, because that's what waves do. Like water waves do that even, they refract. And then Thomas Young saw it as a wave because of interference, and we'll see that again in chapter 8. And then Einstein saw or described the photoelectric effect based on the idea that light is a particle. In short, y'all probably get into this in PChem, but basically the photoelectric effect, if you have a piece of metal and you shine light on it, then in certain conditions you'll get electrons on the metal that will eject. And then you can measure the energy of those electrons. And people said that, well, if you have this light and you just emit more of it, like you have a greater intensity of light, then it will cause the electrons to have more energy when they eject off of the piece of metal. But that didn't happen, right? You would get more electrons, but they would have the same amount of energy. And so what they did instead is that they changed the color of the light. They raised the frequency of the light, and then they found that those electrons, when they were ejected off of the metal, that they had a greater amount of energy. And so Einstein described this by saying that, well, these light is not actually a wave, but it comes in little packets. I think Newton called them corpuscles, but Einstein called them photons. That they have particular amounts of energy, and when you change the frequency of those packets, then you will increase the amount of energy. Those little packets of light are photons. As I say, y'all probably get into that in PChem. Is that right, Joseph? You'll do photoelectric effect? What's that? I'm sorry. Oh, okay. All right. But it was a pretty big deal, and actually that's why Einstein earned the Nobel Prize, not for his work in relativity, but because of his work on the photoelectric effect. He didn't discover the photoelectric effect, by the way. Like, it had been known before, but he described why it occurs the way that it occurs. I met this theorist once, and he said that he never believed data unless there was a theory attached to it. And theorists are sort of that way. And Einstein, of course, was a theorist, so maybe he never believed the photoelectric effect, so he could explain it. But anyway. All right, so let's take this little quick test. Which of these phenomena suggests that light acts as a particle?
Did you ever turn back on a video?
Yeah, I think so. Yep. Which of these suggests that light acts as a particle? Interference, reflection, refraction, or the photoelectric effect? Or some combination of those?
You know, I'm so glad I made it to class. I almost didn't make it, since we have so many cookie questions.
Did we have a lot today?
I'm so glad.
All right, about 10 more seconds. 45, I'll stop. Two and 4, reflection and the photoelectric effect. That's right. So C is the right answer. And remember also, you need to know the people attached to these. So Newton was reflection. Photoelectric effect was Einstein. And then also these others, this is Thomas Young, interference. We'll get into this quite a bit in chapter 8. And then refraction was Huygens. And each of them was right, by the way. Like all of these various attributes of light are true, they occur, and they also represent either wave or particle-like qualities of light.
Did you, the video you didn't finish the last two, you left the last two examples blank.
The last two examples.
Right here, you put that the first one was a dual nature, and then it acts as a particle and sometimes as a
Right, particle. Sorry about that. Sometimes it acts as a wave. Again, we'll get into that later, and we'll actually watch this video. I don't think I put it on there. We'll watch it in chapter 8, because it's more about interference and refraction. Is that where I put in the cat video? Oh, okay. Hope y'all like that.
What was your chat video?
I was going to put in a video, but then I decided not to, and so instead I put in, like, stupid cat video. Or not stupid, funny cat video. Right. I thought it was kind of funny. Alright, let's try this one. Now be clear that this is not drawn to scale. So the way it looks, this looks like 45 degrees, but it's not 45 degrees. It's actually 30 degrees. So it's not drawn to scale. But I want to know now, what is theta 2? And this goes back to our law of reflection. The law of reflection just says that the incident angle equals the reflected angle. That's true for particles and for light. But this is not drawn to scale. Up at 112. A few more seconds. I'll stop at 115. Oh. Going on extra. Yeah.
Since that's the correct answer, the rule
Reflection?
of complementary angles from geometry,
Uh-huh.
that could be applied to this too. That's the rule of complementary and supplementary angles.
Yeah. Yeah. So if that angle is 30, this is 30, that means that this angle has to be 60, right? Because this is a 90-degree angle. That means this has to be 30, so this has to be 60, so this has to be 60. So C is the right answer. All right. But it looks like they're all 45 degrees, right? But it's not drawn to scale. I'll fix that for the exam. If you have something like this, it'll look more to scale. Does that answer your question?
Yes, I just did it with the right answer.
Okay. All right, law of refraction just talks about how the speed of light changes when it enters a medium. If it's moving from a vacuum into another medium, like, glass or water or whatever, the speed is going to slow down. We define that index of refraction, the speed of light. And this index of refraction always has to be equal to or greater than 1. And actually for air and helium, it's not actually equal to 1. It's like 1.000 something. That's a common way, by the way, to determine unknown gases, is to measure their index of refraction, which is fairly easy to do with a simple setup. Let's try this quick test. Remember, the velocity of light is equal to c divided by the index of refraction. C is 3 times 10 to the 8. That's the speed of light in a vacuum. Meters per second. Try to wrap it up, say 15 seconds or so. I'll stop at 225. 225. Guess if you don't know. Alright, that must be right. Let's see. Alright, so first you want to find your velocity, which is going to be this divided by 1.5, so that's 2 times 10 to the 8 meters per second. And then it's just simple kinematics, right? V equals d over t, 2 times 10 to the 8 equals 10 meters over t. And then solving that for t, you get a 5 times 10 to the minus 8. 10 over 2 e to the 8. It's 5 times 10 to the minus 8. Have any more? I think there's one more. Here we were talking about the, we got that whole marching band analogy bit. Yeah, so you imagine these wave fronts that are traveling along, and then when the light enters a medium, it slows down on this side, and then this side keeps going faster, so it's like it bends around. And then these wave fronts will bend as well, and so you can draw the ray like that. And then the reverse happens if you're going from a high index to a low index. All right, this is true also if y'all ever like driven like a bulldozer or like a twin propeller boat or something. A similar thing, like if you speed up one side, it makes it turn. Doing a bulldozer? Twin propeller boat? Okay. So it's the same thing. But I like the marching band.
I like those new, how do you call it, those newer motors, newer lawnmowers where you can...
Like a zero turn, right.
You can shut this one forward.
Maybe that's a better analogy, a zero turn mower. Bulldozer's easier, yeah. Solve this. I think that's where we left off, right? All right, let's try this one using that idea. I understand that the inequalities here aren't written correctly, that the symbols are all mixed up, but which of them describes the relationship between the indices of refraction? You want to find what is the relationship between N1 and N2, and then N2 and N3, and then if necessary, you need to find the relationship between N1 and N3. How are those related to one another? Are they bigger or smaller? No, it doesn't matter. try drawing your wave fronts like this. I'll do the first one for y'all. Here we notice that since it bends in this direction, that means this side must be speeding up. And that tells you that N2 is less than N1 because it speeds up in N2, so it has a lower index. And so you can get rid of some options. D and B it looks like. Alright, just a few more seconds. I'll stop at 220. Let's see here. So I can also find N2 and N3. If I imagine my wave front's coming along here, it speeds up in this direction. That means that N3 is what, bigger or smaller than N2?
Bigger.
It's bigger than N2, right? So looks like that. So if N3 is bigger than N2, that gets rid of C. Yeah, so A is the right answer. Well, look, you can also figure out what are the relationship between N1 and N3. I can take out N2 altogether. So imagine this is N1 and this is N3. I can redraw those rays like this. Right? It's as if this wasn't even here. All right? Like I just remove it completely, and then I can figure out what is the relationship between N1 and N3. So my wavefront comes like this. It slows down here. That means that N3 must be bigger than N1. And let's see if that's true here. N3 is bigger than N1. That's right. All right? And again, I understand these inequalities aren't written correctly. I'll have it written correctly. Let's try this one. We'll wrap up soon. One of the implications of the law of refraction, and actually this is usually called the law of refraction, N1 sine theta 1 equals N2 sine theta 2, where theta 1 is the incident angle, theta 2 is the refracted angle. About 10 more seconds. I'll go to 210, 210. Okay, we're sort of split here. Let me show you something that you can do. I know that N1 sine theta 1 is equal to N2 sine theta 2. And then for this, I can also say the same is true for these two media. That is that n2 sine theta 2 is equal to n3 sine theta 3. So I know theta 1, I want to know theta 3, so I can say then that these two are equal, right? Because these are all equal. If A equals B equals C, then A equals C. So I can say n1 sine theta 1 equals n3 sine theta 3. And so that's going to be n1, which was 1.2 sine of 30 equals 1.1 sine of theta 3. So theta 3 equals the inverse sine of, what, 0.6 over 1.1? What does that equal to? Nobody's telling me. What is it? Okay, so A is the right answer? A is right? Alright, so 33 degrees. Alright. Let's do this last one. We have a couple more minutes. Oh, did I not do the 0.6, 1.1? I get 33 degrees.
Yeah, if you, I took the like 2 significant digits, but if you take the whole thing,
Oh,
I
okay.
rounded just to 32.4. The second time I got exactly 33.
Okay. All right. I mean, sine of 30 is a half. So. All right.
I did it N1 sine. I did the whole workout. I worked it all
Okay. All right. All right. So here we have a guy looking at a star or something in a cup of water.
He's not happy.
Yeah, I always try to make my exams very happy experience, but on this exam, I was grumpy or whatever. So. Okay. So where does he actually see the image of the star?
Well, he lost his star in his water. Come on. He's gonna be angry. It's like, come on, I have to get my hand wet.
All right, looks like we're out of time. I'm going to show you. It's still going, so click in. But notice if you have a light ray that comes out here, it's going to bend away from the normal. And so he'll see the light ray as if it's coming from there. And we know where the image of the star is if we trace that ray back. We'll do this in the next chapter quite a bit. And so the image of the star will appear to the right of the actual star. So C is the right answer. We'll do this next quick test on Wednesday, and then we'll finish this chapter up on Wednesday. I'm having a help session on Wednesday at 2 p.m. That's for the 102 section, so we won't do like cross products and stuff, but a lot of the other stuff that we're doing there will apply to y'all. So if you want to come, it'll be Wednesday at 2 p.m. It'll be down in Beauregard 165. I'll send an email out to the class. If you want to come, that's fine. But I won't be able to do like cross products and stuff like that. And I'm going to be out tomorrow morning, but I'll be in the afternoon. Stop this. Go. Bye, Brittany. Bye, Scott. Bye, Catherine. Bye, John Murray. Have a good day. You graduating this semester then? Yeah. Bye, Tom.
I checked to make sure that the final fell on the day that I could still turn in my grades.
Okay, well, if it's a problem, just let me know. We'll take care of it. All right. Bye, Mary. Have a good day.
See you later.
Bye, Rob.
on a screencast I saw, but I'm pretty sure it was labeled 55, 56, and 57, but it broke into like chapter 2 for some reason.
Maybe you're looking at the 101.
YouTube channel. No, but like broke into information we covered already.
Really?
Yeah, I was kind of confused, but I still took notes on it. I was like, this looks familiar. I was at your YouTube channel somehow.
Mm-hmm. Let me show you. So, if you go to this site, I mean,
So you have to go
this.
No, but
This is the Physics 102 site.
no,
I
but
sent
I
you
didn't
on.
go to that website. I went to a different website. I'm trying to figure out what website I went to.
You might have gone to the 101 site.
And it
I don't know how
brought
you
me to like electricity and whatnot again.
should have. Like, this is, I think this is the website I sent you. You're supposed to be 55, 56, and 57.
Yeah. I was going by these numbers.
Oh, goodness, yeah, 55.
Yeah.
Oh, yeah, that's the, I'm sorry. No, see,
I was
they're-
going by these numbers. So,
yeah, see, they're numbered here.
Oh.
55, 56, 57.
that's a problem.
Yeah, I'm sorry. I guess I should have been more, I didn't even know they had numbers here.
Yeah. I just saw numbers on the left. Oh, look, is this up? Look. I'm like,
Mhm.
is this? This doesn't seem right. All right, okay.
All right, Andrew, I'm sorry for that.
Is this all right? Just
All right, have a good day, okay?